Hello everyone, I am Anna. I am a PhD candidate at ECU University. And the reason that I'm bringing up validation of fire records today is because the central topic of my PhD is looking at the relationship between fire history and fire severity. And today I'd like to demonstrate how useful were the Google Earth Engine APIs in combination with other GIS tools to allow me to validate the fire history records, which is the main data set for my study. So climate change has been a big issue and has been increasing the number of extreme events, particularly in the Mediterranean type of climate regions. So the southwestern Australia, where Java Forest is located, there has been a significant number of wildfires and prescribed burns over the last decades. So in this context, it's very important to have accurate and complete data sets. So if we have long-term historical data, it would allow to provide accurate future fire behavior predictions, and also to inform appropriately fire management. So the problem with the situation is that although fire events has been recording over many decades, particularly in southwestern Australia, there are a number of inaccuracies with this fire history database, which does not provide a reliable set of data for this type of study. So one of the examples is that because of the involvement of numerous government agencies being responsible for recording and registering those data sets, the number of inconsistencies across the years and the location in the state, it's quite large. And the number of incomplete data and incomplete attributes, it's also significant. So the problem in this situation is that limits to conduct appropriate research in fire ecology and challenge fire management, as well as restricts the understanding of fire regimes, such as the study that I've been doing in my PhD. So, for example, I'd like to demonstrate in this figure. So to contextualize, some of you might be familiar with some of this data sets. So in the 2015, the map on my right-hand side, it shows like the boundaries and the location and the date of particular prescribed burn. So in 2022, the same area was burnt again, but the differences between the two maps is the improvement in the accuracy in mapping them, because since many factors influencing the behavior of fire spread, but one of the main elements is the patches that are unburned with a particular burn perimeter. So because of the improvement in the methodology used, the technique used to map those fire boundaries, the whole location of the fire, you can see that in 2022, there has been an improvement showing the patchiness. So the problem is the majority of the records in the fire history database, particularly records prior to 2000, are mostly in this situation. So what I did is to find appropriate method to pretty much fix this data set. So in this sense, APIs were very effective, and they demonstrated were very efficient in me to conduct this study. So than traditional GIS software, because the main reason is because dealing with historical fires, you're dealing with a large data set, spatially and temporally. So that has demonstrated like good time efficiency, where you can access different imagery in the context of fire study, You can access different imagery from multiple sensors, which allowed, for example, to access, for example, the right, in this case, Landsat imagery for the particular period and year that you're studying. It allows to repeat the measurements because you can create a model for a particular fire and then repeat over as many fires as you would like to, and automate the process so that you can have minimal user intervention and save a lot of time as well. And also the implementation of the use of APIs in this method provided incorporation of machine learning, which improved the number of training data set, where in this case improved the accuracy in mapping fire severity. It also allowed me to combine several different data sets from different agencies and different satellites, such as MODIS and other data sources, and also provide area calculations, which was one of the main elements that helped me to to validate the fire database. So, although the fire history database contains numerous attributes, I focused on the validation of fire boundaries and dates. This says for 340 fires, because they were the two main elements that would allow for me to study elements of fire history, such as fire frequency, fire return interval, number of fires, and fire severity, which was the target variable. So for that study, the location that was chosen was Mundaring Catchment, that's located in the Jarrah Forest in southwestern Australia. I used the Landgate Fire History Database over 32 years, so that started from 1990 until 2021. And I included both prescribed burns and wildfires, and I also included actually the fires that do not have any description, since the database is incomplete in some occasions. And I would like to emphasize that for every fire perimeter, which in the case of the fire database, it's given as a polygon, like as a vector, it contains one date per perimeter, which would demonstrate that fire event happened on that particular date. But it does not discriminate if it was the first date of the fire or the date of the highest fire intensity or the end of the fire. So I used different satellites and sensors, such as Landsat, MODIS, and I also used both Python, JavaScript, in Google Earth Engine platform, and 7 different spectra indices. So here I demonstrate the tools and the main data that I used for this process of validation of both burned area, the burned area inside of the fire perimeter, and to detect the most approximate dates, both start and end date of all 340 fires. So I used desktop GIS to do the pre-processing of the fire history database, to which I focused in grouping by year, the fires by year of registration. I processed each fire individually, and also created increased the area of the size perimeter, creating a 2 kilometers buffer. So I used Landsat imagery, which was the basis of the spatial scale of my study. So everything was focused in mapping the fires across 30 meters, 30 by 30 meters, 900 square meters. And I calculated the spectral indices in each fire perimeter. I conduct a phenological calibration to account for the changes in the vegetation between the period of collection between the pre-image and the post-fire image. And then I calculate fire severity, and I also managed to calculate fire occurrency, which is in this case is the process of validating the fire boundaries. I also used MODIS imagery to detect the dates of some fires, particularly the fires that are after 2000. And I also used the MODIS imagery to test the performance of the entire method that I developed using Landsat to detect the most approximate dates. I used some datasets from DEA, Digital Earth Australia, such as bare soil and vegetation, herbaceous vegetation, to mask out from the image and improve accuracy because there are confounding factors in the severity mapping. I used random forest to classify severity in 5 classes, where I could utilize over 10,000 data samples extracted from IRA images to be able to train the model and classify severity. And in this little image, it's just an example how I classify severity per pixel for the whole catchment. And I promoted IRA calculation. So after calculating severity in each fire perimeter, I managed to calculate what was the size of each, the total area of each severity class in each fire perimeter, where I created like a binary reclassification. So I separated all pixels that were unburned to the pixels that were burned, and then that was the main mechanism that allowed me to identify what was the area burned within the fire perimeters. And then I went through and did the fire date detection, which was a bit more complicated. So just I can very briefly say that to be able to detect the fire dates, I had to scan through the entire year. So I created like 23 hypothetical dates, like both pre and post fire dates that would run across the year. So that created like 23 date ranges. So in every date range across the year, I could run through the same calculation and identify in which of those 23 date ranges the fire happened. So in this image, it's the workflow of the semi-automatic method that I used for both detecting the burned area within the 300 fire perimeters and the fire date. So the reason that the main aspect of this diagram is that it runs through 2 different cycles. So because I have numerous fires, and for every year I have a certain number of fires. So the first cycle in there, it repeated to all fire perimeters that happen in the same year. So, and then the larger circle, it shows the repetition of the whole process over the 23 date ranges to be able to identify in which of those 23 date ranges the fire had happened in that year. So in the process to exemplify, so I would extract 1 fire perimeter from a particular year. So I would choose a year, extract 1 fire perimeter from that year, create a buffer around the fire, set the hypothetical date ranges. So I started from like 1st of January until 31st of December at every 17 days because of the spatial resolution, temporal resolution of Landsat. And then I run the whole process. So I located the appropriate Landsat imagery, create the pre and post fire imagery for that fire perimeter for that particular date range. Apply the mask, so removed bare soil, herbaceous vegetation, calculated the 7 spectral indices inside of the fire perimeter and from the buffer, so it could conduct the phenological calibration next. After the calibration, I classified in the 5 severity classes, calculated the area, did a binary classification, and then the first output for the first perimeter in the first date range would be the identification if that fire perimeter was burned on that perimeter or not. So after that, it runs through again for the next 22 times in the larger circle. So the main results in here that we could validate successfully the fire history database. And in this example, we have the green area, which demonstrates the unburnt region, and the other colors represents the burnt region. So it did validate it accurately, so we could identify that not all fire perimeters that were in the database were actually burnt. But what's more surprising is that each fire perimeter was burnt multiple times. So although the fire history database provides only 1 date, there were found multiple dates in the same fire perimeters, showing that the area was burned up to different dates on the same year. And it's another example showing some fires in 1991. So the green fire at the bottom was an example of a fire perimeter that was added in the fire history database, but it was actually unburned. So the problem with that is because we wanted to, based on this database, to be able to identify where it was burned and when, so we can improve our data set and make predictions for future fire behavior. So with this method, I was able to find that 72% of the area was burned within the fire perimeters. Only 45% of the dates that I detected compared to the dates of the fire history database match. And 56% of the dates were incomplete, mainly because the fire history database includes only one date, and most of the fires, they have multiple dates. And the situation with the dates are very important because if we don't have the most approximate date of the fire, it enables us to find the closest imagery to be able to map severity appropriately. Because if we have an imagery 1 year later, you're not going to be able to represent the severity of that fire as accurately due to the vegetation recovery. So the Google Earth Engine APIs were really good to improve the fire history databases, and that's essential for other researchers that intend to conduct research in this area. And importantly, this method can be reproduced for fire records across anywhere in the world, pretty much. Thank you very much. That's my presentation.